My name is Ashley Foreman, and this is my Lab 2 motion of a falling object. And so in this experiment, we were asked to observe the motion of an object that is dropped from rest and falls somewhat slowly, and that object was a crumpled piece of paper. The motion of the experiment was observed using a tracker, as well as two computer models, one using only gravity and one using gravity and drag force. This experiment aimed to evaluate the effects of gravity and drag force on a falling object to best model through GlowScript the motion of the falling object observed in tracker. And so the fundamental physics principles used is Newton's second law and the derivatives of the velocity update formula and the position update formula, as well as gravity force, which is negative mg, and drag force. And so in this experiment, you can see me dropping the paper ball. And so the system is the paper ball and the surroundings is everything else. The ball had an initial mass, or just a mass of 0.0045 kilograms, and the diameter of the ball was 0.05 meters, and that was used to calibrate this video. The axis is tilted due to camera distortion, and the position versus time graph has a negative slope with a negative square line of best fit, like with this curve here. And so the experiment results, this is what that shows. This is that negative curve and that negative slope, and here's the data that came with that. And so the computational model, the initial conditions, I have that same mass, so it's 0.0045. The ball's position starting at 0, ball's velocity starting at 0, g equals 9.8. The j of hat vector is 0, 1, 0, and there is b is equal to 0 because it's for gravity only. There is no drag in this model. And so I did while t is less than 0.6 seconds, and this is because the data that I got in tracker ended at 0.6 seconds. Then we have the weight force, which was put in. It's the negative ball mass times g times j hat, and F net is equal to weight force only. That's the only force acting on it. The ball's velocity is updated using the velocity update formula with Newton's second law, and so is the position using the position update formula. And so here's this predicted motion. The velocity decreases at a constant rate due to the constant rate of negative acceleration due to gravity. And the slope of the position versus time graph is negative and decreasing, meaning that the magnitude of the velocity is decreasing. Or the magnitude of the velocity is increasing. This line gets steeper. And so this is the computational model of gravity and drag. And so it has the same mass, same initial position, but the only difference is that b is equal to 0.00301. And I found that using the endpoint of the tracker data. And so it has the same ending time, but the difference here is that we have the drag force, and that is equal to b times the magnitude of velocity squared times j hat. And so F net is equal to the weight force times the drag force. And so it's still velocity update formula, position update formula, but we also have this arrow scale, and so that comes into play. And so this arrow scale shows the force of drag here and the force of gravity here. And as you can see, the velocity versus time, this graph has a slope. The slope of this is slowly flattening, and that's due to the drag force. And this position versus time is slightly different. And so here's both models versus the experiment. So this is experimental, drag, and gravity. And so the closest model is the drag plus gravity model. And it still underestimates, as you can see with this gap here, but the model without drag has a much steeper slope, and therefore it is predicted the fall of the ball to be at a much faster rate. And so what does terminal velocity mean relative to this experiment? So with this gravity model, the velocity is constantly decreasing, but with the gravity and drag model, the slope of this is slowly flattening out. And when you watched on tracker with the ball, which is like what I'm talking about here, you could see these forces, this drag force slowly increasing and these becoming more and more equal. And the point in which those become equal is when the terminal velocity happens. And so the gravity and drag model accounts for this terminal velocity, but the gravity model alone does not. And so what if the object was thrown downwards instead of dropped? And so using the second computational model, I changed the initial conditions to be with a starting velocity vector of 0, negative 1, and 0, as if it had been thrown. And so essentially it looks exactly the same as the normal gravity and drag graph. It's just that it starts at a velocity, and so it reaches its final position faster because it's starting faster and it's the acceleration, and so it's going to be going at a faster speed, and it'll reach its terminal velocity maybe a little faster, but really it ends up being all about the same. And so the possible sources of air through here is likely due to the fact that this is a paper ball, and so since it's crumbled, it has a lot of different curves and edges in places in which this drag force cannot be correctly calculated. And it could have also just been with the way I did it in Tracker and inaccurately placing the midpoint.